Welcome members to this lesson. Today we are going to see how do we handle this proof by induction when we are given a summation notation sign. And before we proceed, make sure you have subscribed to receive notification whenever I upload more videos. So members, from here, how do we handle this? It means that we are starting from 1 up to n. So these are always integers. So when r is 1, we shall be having, when r is 1, I'll be having 1 cubed. Be having 1 cubed plus, because I'm summing, the next integer will be 2, so I'll be having 2 cubed plus, the next integer will be 3, which will be now 3 cubed plus, up to when I reach the last integer. Here they are telling me that the last integer is n. I'll be having n cubed, but all of this is equaling 2, they're telling me that it's equaling 2 n squared over 4 into n plus 1 squared. So now we divide this into, this one we call it the left hand side, this one we call it the right hand side. So we prove now it's true for n is equal to 1. Now when n is 1, let us see. It's that my left hand side will be, I have only 1 cubed, which is 1. Now on my right hand side, so when I put in n is 1, I have 1 squared, which is 1 over 4 into 1 plus 1, that's 2, 2 squared, that is a 4, which will be also a 1. So the left hand side is equal to right hand side. When n is 2, I have 2 terms, so I take the first 2 terms. I'll be having now my left hand side equaling to 1 cubed plus 2 cubed. This would be 1 plus 8. 2 cubed is 8, which will be a 9. Now my right hand side will be n is 2. Now I substitute here 2 power 2, that is a 4. So I have 4 over 4. Then 2 plus 1, I get 3, the whole square. This will be 1. 3 squared is 9, so this is equal to 9. You can go on to prove when n is equal to 3. When n is equal to 3, you type the first 3. And then you substitute the side, n is equal to 3. You see what you get. Now, we just need to prove for this 2. Then next step, we assume it's true for n is equal to k. Now when n is equal to k, I'll be having 1 cubed plus, where there is n, I put k, having k cubed equaling to, now k squared over 4 into now k plus 1 squared. Now I prove it's true for n equaling to k plus 1. Now for n equaling to k plus 1, here is some concepts. From here up to here, the number of terms are k terms, and their sum is this. Now, if I'm to add on another term, if I add this term this side, a term this side, it means I also add a term this side. Now, how do I get to the term? So from here, I first write this is 1 cubed plus 2 cubed plus 3 cubed plus up to k cubed. Now these are k terms. Now I want to add on a 1 term so that I have k plus 1 term. Now I see from 1 to get a 2, add a 1 to get a 2. From 2 to come to 3, add a 1. And like that. From a 3 you come to 4 cubed, you add a 1. Now, if I have k cubed, it means that I'm going to say, to get another term, I will say this will be k plus 1 cubed. That's how I will get another term. Now these are k terms plus 1 term. The whole of this is 1 term. Equaling to, we said from here up to here, our sum was k squared over 4 into k plus 1 squared. When you add all of these ones, the whole of these, we say this is the sum. It means that the whole of this is this, but I'm adding this. So if I add it on the left, it means that I also add it on the right. So this will be now k plus 1 cubed. Now balanced it. Now we simplify this. My right hand side now is equaling to, this I have k squared into k plus 1 squared, then plus k plus 1 cubed over 4. So I'm going to get the LCM. You just get by cross multiplying up and down. And I multiply this here, I'll be adding k squared into k plus 1 squared plus, this will be 4 into k plus 1 cubed. Now the whole over 4. Now you see that this bracket is common here. You see this, when I factorize it out, I'll be adding k plus 1 squared. It's common. Here I'm remaining with k squared then plus. If I remove k squared from here, I remain with 4. Then this one reduced to k plus 1. I'll be remaining with 1 bracket if I remove the 2. Then the whole this, we are dividing it by 4. Now, you can open the brackets here. So we are having k plus 1 squared into k squared plus, okay, then plus 4. Open the brackets there, the whole over 4. Now, so this is the perfect square. We can write this as k plus 2, the whole square. If I expand this, I get this. So this will be now k plus 1 squared over 4 into k plus 2 the whole square. Now, we don't want any k in our proof, so we remove the k. How do we remove it? We come from here, we say our k plus 1 is equal to n. Make k the subject. I want to remove k, so I make the subject. My k becomes n minus 1. So putting them here, I'll be adding now into my k is n minus 1, but I'm adding the 1, the whole square, into now k is n minus 1 plus 2 squared. This is 4. So this will cancel. I'll be adding n squared over 4 into, when I simplify negative 1 plus 2, I have 1. So n plus 1 the whole square. And you see, this is the proof we have. And then you conclude that since it's true for n is equal to 1, 2 and k plus 1, then it's true for all positive integers. So I'm going to add another video about these ones, but please don't forget to subscribe to the YouTube channel. I wish you the best.